Okay, let's do a few practice problems on here. All right, so let's consider the following experiment. We're going to roll a fair six-sided die 3 times in a row. Well, the first thing I want to know is this independent or dependent? Well, these are independent. The outcome of the first roll of any roll is not affected by a previous roll. Okay, so what we're trying to find here is what is the probability of rolling an even number on all 3 rolls. So the probability of 3 evens is what we're looking for. Okay, so let's see, if we're rolling a fair-sided die, it can either come up with a 1, a 2, a 3, a 4, a 5, or a 6. So there are 6 possible outcomes, and of those, there are 3 evens. Okay, so let's figure this out. If we want the probability of 3 evens, that means we need to find the probability of an even on the first roll times the probability of an even on the second roll times the probability of an even on the third roll. If it was 4 rolls, we'd just keep going. Well, for each of these, we know that the probability of an even is 3 out of 6. Which is 1/2. So the probability of an even on the first is 1/2. On the second, since it doesn't matter what happened, and on the third, so that gives me 1/8. Now once again, this can be changed to a decimal, 0.125 or 12.5%. So just read the instructions and see if you're supposed to leave it as a fraction or an unreduced fraction or whatever's going on. Okay, let's consider the following experiment. You are drawing a card from a deck of 52, replacing it in the deck, and drawing another from the deck. Okay, we are replacing it, which means these are independent events. And again, the outcome of the second pick is not affected by the first pick. Why is that? Because we're putting it back. Okay. So we are looking for the probability of ace and ace, which means we're going to find the probability of an ace times the probability of an ace. Well, we know the probability of an ace. If you look back at your deck of cards, there are 4 aces out of a standard 52. There are 4 aces out of 52 since we put it back. Now once again, if you're doing this as a fraction, you can do it as an unreduced fraction. 4 times 4 is 16. I don't know what 52 times 52 is. 2704. And if that's a reduced fraction, that is 1/169. Again, This would be a fine answer if I asked you for a fraction. If I ask you for a percent, if I do the division, this is approximately 0.00592 or 0.592%. Okay. All right, consider the following experiment. You are drawing a card from a standard 52 deck, placing the card on the table, and then drawing another card. These are dependent because it is without replacement. So the outcome of the second draw is affected by the first draw. Okay, so what is this is the probability of an ace given an ace, which means the probability of an ace times the probability of an ace given the ace on the first. All right, so the probability of an ace is 4 out of 52. But now if you think about this, if we have our deck of cards, and let me see if I have my thing real quick. So here's a deck of cards. If I have 4 out of 52. But if I draw an ace and I don't put it back, then I only have 51 cards left and only 3 are aces. For my first draw, I had the whole deck and I had four possible aces. The given event is that you drew a card and it was an ace. I don't know which one it is. This one's easy to put my thumb on. So what do I have left? Now I have modified my grouping, so I have only 51 cards left and only 3 of them are aces. So this is 3 over 51. Okay, so that becomes 12 over 2652, which if I do the division becomes 0.00452 or 0.452%. Okay. All right, let's talk about M&Ms. All right, on this one, let's see. You have a bag of M&Ms that are 6 red, 5 yellow, 2 green, 1 blue, and 4 brown. Okay, so I'm going to do some drawing. Again, you know me, I like a very visual thing. So I need 6 reds. Five yellow. 2 green, 1 blue, and 4 brown. I don't have a brown pen. Huh. Okay, well, this is the closest I've got. Let's call them purple. Who would have ever thought I'd want a brown pen? Okay, so 1, 2, 3, 4. Okay, now the first thing we have to do is decide if it's independent or dependent. Okay, so we've got this bag of M&Ms. We select an M&M and eat it. This is dependent because it is without replacement. Okay, so what is the probability of drawing 2 yellows? So let's see what we've got here. So the probability of a yellow given a yellow. So that's going to be the probability of a yellow times the probability of a yellow given the first yellow. Okay, so let's see. How many of you got 4, 8, 12, 16, 18? So I have a total of 18 M&Ms. So the probability of a yellow, I know, is going to be something out of 18. So 1, 2, 3, 4, 5. So there are 5 yellows out of the 18. All right, but now one of the yellows is gone because I ate it. So there are only 17 left in the bag, and there are only 4 yellows. So if I do my probability, this becomes 20 divided by 306, which becomes 0.0653 or 6.53%. Okay, so what is the probability of drawing a red followed by a green? Okay, so what do we want to do? We need to find the probability of red of a green given a red. So I need the probability of a red times the probability of a green given the first one is a red. Okay. All right, so the probability of a red, we're starting out with a full bag. We have 6 out of 18. All right, then look at the green. I've got a red one that is gone. So now I only have 17 M&Ms left in the bag, and there are 2 greens. So this becomes 12 out of 306, which is 0.0392 or 3.92%. Okay, so what is the probability of drawing 2 blues? So I need the probability of a blue given a blue. So that becomes the probability of a blue times the probability of a blue given the first blue. Okay, well, let's look at our M&Ms here. We have 1. So the probability of a blue is 1 out of 18. But let's say now that I eat it. Oh, and I should have put it on the end. There are only 17 remaining, and there are no blues. So this becomes 0 out of 306, which is 0, or 0%. It can't happen. There's no way you can draw 2 blues if there's only one in there and you've taken it and eaten it. Okay, and our last problem. Consider this situation. So you're going to select people to serve on a 3-person committee from a pool of 10 men and 10 women. All right, well, now this is one where, you know, these people are not in a bag, but they're in a room. Now, once they've been selected to serve on the committee, they're not going to be selected again. So this is going to be dependent because it is without replacement. Okay, once somebody's been selected, they're no longer in the pool. They're already on the committee. Okay, so what is the probability of selecting an all-male 3-person committee? Okay, well, I may want to do this again as well. So let's see. I've got 10 men, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I have 10 women. So we want to find the probability of male, male, male. Okay, so we have to find the probability of a male times the probability of a male given the first male, and then the probability of a male given the second male. Okay. So the probability of a male is, well, there are 20 total, so that would be 10 out of 20. But then one of the men is gone. So this becomes 19. So there are now 9 out of 19. So another man is gone, and we're down to a pool of 18. So there are 8 men remaining out of the 18 category. Okay. Well, this is 1/2, so I'm just going to write this as 1/2 and do my multiplication. So this is 1/2 times 9 over 19 times 8 over 18. 9 times 8 is 72. 2 times 19 times 18 gives me 684. If I want to write that as a decimal, this is 0.1053 or 10.53%. Okay, the end. We'll do 7C next time.